Welcome. The Internet's secret handshake. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we are going to learn about how your web browser and websites do a secret handshake to keep your information safe. Every time you visit a website that starts with HTTPS and you see that little lock icon in your browser, your computer and the website are using something called TLS 1.3 to create secret codes. And guess what? TLS 1.3 uses HKDF, the secret code-making machine we learned about before. Think about when you visit a website to check your email or buy something online. Your computer needs to send your password or credit card number to the website, but you do not want bad guys to see this information as it travels through the internet. So your computer and the website need to agree on secret codes to scramble the messages. But here is the tricky part. They need to agree on these secret codes while talking over the internet where bad guys might be listening. How do they do it? That is what we are going to learn today. TLS stands for Transport Layer Security, and version 1.3 is the newest and most secure version. It is like a recipe that tells computers exactly how to create secret codes safely. The recipe has several steps, and at each step, HKDF is used to turn secrets into keys. We will walk through this recipe step by step so you can see exactly how it works. By the end, you will understand how billions of people stay safe online every single day. We will use real examples with actual numbers and outputs so you can see what is really happening. This is not magic, it is mathematics and clever design by very smart security experts. Let's dive in and see how the internet keeps your secrets safe. The TLS handshake. Hello messages. When your browser wants to talk securely to a website, the first thing it does is exchange hello messages. This is like when you meet someone new and introduce yourselves. Your browser sends a client hello message, and the website sends back a server hello message. These messages are sent in plain text, which means anyone watching can see them. But that is okay because these hello messages do not contain any secrets yet. They are simply the computers agreeing on how to create secrets. In the client hello message, your browser sends several important things. First, it sends something called client random, which is 32 bytes of completely random numbers. Your browser generates this using a random number generator, and it might look like beginning with a 1 ending with H8, and so on for 32 bytes. Second, your browser sends a list of cipher suites it knows how to use. A cipher suite is like saying I know how to speak English or I know how to speak Spanish. The browser is telling the website which encryption methods it understands. Third, and this is super important, your browser sends something called a key share. This is your browser's public key for something called ECDHE, which stands for Elliptic Curve Diffie-Hellman Ephemeral. Do not worry about the complicated name. Just think of it as your browser sending half of a secret puzzle piece. The browser keeps the other half private. This public key might be 32 bytes of data that looks random, like beginning with 80 and ending with 93, and so on. The website receives the client hello and then sends back a server hello message. In this message, the website sends its own server random, which is another 32 bytes of random data. The website also picks one cipher suite from the list the browser sent, like saying, okay, we will speak English together. Most importantly, the website sends its own key share, which is its public key for ECDHE. This is the website's half of the secret puzzle piece. Now here is the clever part. Your browser has its private key and the website's public key. The website has its private key and your browser's public key. Both of them can now do some special mathematics called elliptic curve cryptography to compute the exact same secret number. This secret number is called the shared secret, and it might be 32 bytes that look like beginning with 8B and ending with 0D and so on. Nobody else can compute this secret because they do not have either of the private keys. This shared secret is what we will feed into HKDF to make all our encryption keys. Pretty clever, right? The early secret mystery. Now we are ready to start the HKDF key schedule. The first stage is creating something called the early secret. This is where things get interesting and a little bit mysterious. If you are connecting to a website for the first time, your browser does not have any secrets from previous visits. So the TLS recipe says to create the early secret by calling HKDF extract with both the salt and the input key material set to 0. That is right, zeros. You might be thinking, wait a minute, if we put zeros in, don't we get zeros out? That is a great question. The answer is no, we don't get zeros out. Remember how HMAC works? Even when you give it zeros as input, HMAC does special operations inside. It XORs the key with the iPad, which is the number 36 repeated, and it XORs the key with the OPAD, which is the number 92 repeated. So, even though we start with zeros, the actual data being hashed is not zeros at all. Let me show you with real numbers. When we do HKDF extract with salt equal to 32 zeros and input key material equal to 32 zeros, we are really doing HMAC 256 with key equal to all zeros and message equal to all zeros. HMAC pads the key to 64 bytes of zeros. Then it XORs with iPad to get 64 bytes of the number 36. Then it concatenates our message, which is 32 bytes of zeros, and hashes all of that. The result is definitely not 0. Then it takes the original key, XORs with OPAD to get 64 bytes of the number 92, concatenates the previous hash result, and hashes again. The final output is the early secret, and it looks like this, beginning with 33 ending with 92 AC. Definitely not 0. This is the magic of hash functions. They take any input and scramble it into something that looks completely random. So, even though we put in zeros, we get out this big hexadecimal number. Now you might ask another great question. If everyone knows we used zeros to make the early secret, is that not insecure? Does that not mean everyone can compute the early secret? The answer is yes, everyone can compute it. And that is perfectly fine. The early secret by itself is not protecting anything. It is just a starting point, like the first step in a recipe. The real secret, the ECDHE shared secret we computed from the key exchange, has not entered the system yet. That comes in the next stage. The early secret is like preheating an oven. Everyone knows the oven is at 350 degrees, but that does not reveal your secret recipe. The early secret sets up the structure for HKDF, but the actual security comes later. The handshake secret gets real. Now we move to the most important stage, where the real secret is introduced into the system. This stage is called creating the handshake secret, and this is where the ECDHE shared secret that we computed from the key exchange is finally used. Remember that shared secret? It was the special number that only your browser and the website can compute because they both perform the calculations using their private keys and each other's public keys. But we do not just throw the shared secret directly into HKDF extract. First, we need to create something called derived from the early secret. We do this by calling HKDF expand label with the early secret as the input, the label derived, no context, and we ask for 32 bytes of output. HKDF expand label is a special version of HKDF expand that TLS 1.3 uses. It adds a structure to the info parameter that includes the length, a label that starts with TLS 1.3 space, and any context data. So we call HKDF expand using the early secret as the PRK, and the info is a structured message that says length equals 32, label equals TLS 13 space derived, and context is the hash of an empty string. After we do the HMAC operation, we get out a 32-byte value. This is our derived value, and it becomes the salt for the next HKDF extract operation. Are you following along? We used the early secret to make a derived value, and now that derived value will be the salt. Now for the big moment. We call HKDF extract, with the salt equal to derived, and the input key material equal to the ECDHE shared secret. Let us say our shared secret is the value beginning with 8B and ending with 2D. We put this into HKDF extract as the message, and we use our derived value as the key for HMAC. We do all the HMAC operations, the padding, the XOR with iPad and OPAD, the double hashing. The output is the handshake secret. This handshake secret might look like beginning with 1D ending with AC. This value is super secret. Nobody else can compute it because nobody else knows the ECDHE shared secret. Even if bad guys are watching all the messages between your browser and the website, they see the public keys, but they cannot compute the shared secret. They would need to break the mathematics of elliptic curves, which is basically impossible with today's computers. So now we have a handshake secret that is truly secret. This is the secret sauce that will protect all the rest of the handshake. From this one handshake secret, we will derive multiple keys for encrypting and authenticating the rest of the TLS handshake messages. This is where the security of TLS really comes from, not from the early secret which was just zeros, but from this handshake secret which includes the truly random ECDHE shared secret that only the browser and website know. Stage 3. Making handshake traffic keys. Now that we have the handshake secret, we can start making actual encryption keys. We need to make separate keys for the client, which is your browser, and separate keys for the server, which is the website. We use HKDF expand to create these keys from the handshake secret. But there is one more ingredient we need to add, the transcript hash. This is really important for security. The transcript hash is a hash of all the handshake messages sent so far. We take the client hello message and the server hello message, concatenate them, and hash them with SHA-256 or SHA-384. Depending on which cipher suite was chosen. This hash might look like, beginning with B3 and ending with A21. Why do we hash all the messages? Because this binds the keys to the specific handshake that is happening right now. If a bad actor tries to trick your browser by changing any of the handshake messages, the transcript hash will be different, the keys will be different, and the connection will fail. This protects against man-in-the-middle attacks. To make the client handshake traffic secret, we call HKDF expand label. We use the handshake secret as the PRK. The label is CHS traffic, which means client handshake traffic. The context is the transcript hash, and we ask for 32 bytes. The info structure includes the length, the label TLS 13 CHS traffic, and the transcript hash as context. We do the HMAC operation, and we get the client handshake traffic secret. This might be a value beginning with B3 and ending with 21. We do the same thing to make the server handshake traffic secret, but we use the label SHS traffic instead, which means server handshake traffic. Everything else is the same. Same handshake secret, same transcript hash, same length. But because the label is different, we get a completely different output. This might be something like beginning with a 2 ending with 1C. Notice that the client and server traffic secrets are completely different, even though they came from the same handshake secret. This is the power of using different labels in HKDF expand. The labels create domain separation, so that keys for different purposes are guaranteed to be different. Now, your browser will use the client handshake traffic secret to encrypt messages it sends, and the website will use that same secret to decrypt those messages. The website will use the server handshake traffic secret to encrypt messages it sends, and your browser will use that same secret to decrypt those messages. But we are not done yet. These traffic secrets are not the actual encryption keys. They are like master secrets for the handshake phase. In the next step, we will use HKDF expand again to derive the actual AES keys and IVs that will be used by the AES GCM encryption algorithm. We are building a tree of secrets where each level is derived from the previous level using HKDF. This hierarchical structure is what makes TLS 1.3 so organized and secure. Deriving actual encryption keys. Now we will turn our traffic secrets into the actual keys that will be used by the encryption algorithm. Remember, the client handshake traffic secret and server handshake traffic secret are like master keys. Now we need to derive the specific keys for AES encryption and the initialization vectors, or IVs, that go with them. This is where HKDF expand comes in again, and we will use it multiple times to create different keys for different purposes. Let's focus on the client side first. We have the client handshake traffic secret, which might be beginning with B3 and ending with 21. From this one secret, we need to derive two things: the encryption key and the IV. The encryption key is what AES will use to scramble the data. The IV, or initialization vector, is a random starting value that makes sure we get different outputs even if we encrypt the same message twice. This is important for security. To make the client handshake encryption key, we call HKDF expand label with the client handshake traffic secret as the PRK, the label key, no context, meaning an empty string, and we ask for 32 bytes if we are using AES 256, or 16 bytes if we are using AES 128. Let us say we are using AES 256, so we need 32 bytes. The info structure includes the length, which is 32, the label TLS 13 space key, and empty context. We do the HMAC operation, and we get the encryption key. This might be the hex number beginning with DB and ending with CA8. To create the client handshake IV, we do almost the same thing, but we use the label IV instead of the key. We ask for 12 bytes, as that is the standard IV size for AES GCM. The info structure includes a length of 12, the label TLS 13 space IV, and an empty context. After the HMAC operation, we get the IV, which might be beginning with 5B ending with 5F. Now we have everything we need for the client to encrypt messages during the handshake. The client will use the AES 256 GCM algorithm with a key beginning with DB ending with CA, and an IV beginning with 5B ending with 5F. We do exactly the same process for the server side. We take the server handshake traffic secret and derive the server handshake key using label key and 32 bytes. We get a different key because we started with a different traffic secret. Then we derive the server handshake IV using label IV and 12 bytes. Now the server has its own encryption key and IV. When your browser sends an encrypted handshake message, it uses the client keys. When the website sends an encrypted handshake message, it uses the server keys. Both sides can decrypt messages from the other side because they both derive the same keys using the same HKDF process. Pretty organized, right? Stage 5. Application data keys. After the handshake is complete and your browser and the website have verified each other, they are ready to send your actual data like your email messages or credit card numbers. But they do not use the handshake keys for this. Instead, they derive new keys called application data keys. This separation is important for security. If somehow the handshake keys got compromised, the application data would still be safe because it uses different keys. To create application data keys, we first need to create what's called the master secret. This is similar to how we created the handshake secret. We start by deriving a value, which we'll call derived, from the handshake secret. We use HKDF expand label with the handshake secret as the PRK, using the label derived, an empty context, and 32 bytes. This gives us a new derived value that will serve as the salt for the next extraction. Now we call HKDF extract to make the master secret. But here is something interesting. The input key material is 0. That is right, we use zeros again, just like we did for the early secret. You might think, wait, if we are putting in zeros, How is this secure? Remember that the salt is the derived value which came from the handshake secret, which came from the ECDHE shared secret. So even though the IKM is 0, the salt carries all the security from the previous stages. The master secret inherits security from the handshake secret through the salt. After we compute the master secret using HKDF extract, with salt equal to derived, and IKM equal to 0, we get a new 32-byte value. This master secret is what we will use to derive all the application traffic secrets. Now, we are ready to make the client application traffic secret and the server application traffic secret. But there is one more ingredient we need: the transcript hash of the entire handshake up to this point. The transcript hash now includes the client hello, server encrypted extensions, server certificate verify, server finished, and client finished messages. Basically everything that happened during the handshake. This is much more data than before, so the transcript hash is binding the application keys to the entire handshake conversation. We hash all of this and get a transcript hash value. Now we use HKDF expand label to derive the client application traffic secret 0. The 0 means this is the first generation of application keys. TLS 1.3 allows keys to be updated during a long connection, so there might be client application traffic secret 1, 2, 3, and so on later. But for now, we start with 0. We use the master secret as PRK, label CAP traffic, which means client application traffic. The context is the full transcript hash, and we get 32 bytes. This is the client application traffic secret 0. We do the same with label SAP traffic to get the server application traffic secret 0. From these traffic secrets, we derive the actual AES keys and IVs, just like we did for the handshake keys, using labels key and IV now. All your actual data will be encrypted with these application keys. The Complete HKDF Chain Visual Summary. Let's take a step back and look at the entire HKDF chain from start to finish. This helps you see the big picture of how all the secrets flow through the system. We start with just the ECDHE shared secret and some random numbers, and through a carefully designed series of HKDF operations, we end up with multiple encryption keys that protect your data. Each step builds on the previous step in a secure and organized way. At the very beginning, we have the early secret, which is created from zeros. This is just a placeholder that sets up the HKDF structure. Then we derive a value from the early secret. Next comes the critical step, where the ECDHE shared secret enters the system. We use HKDF extract with salt equal to derived and IKM equal to ECDHE shared secret to create the handshake secret. This is where real security begins, because the ECDHE shared secret is truly secret and truly random. From the handshake secret, we derive the client handshake traffic secret and server handshake traffic secret using HKDF expand with different labels and including the transcript hash of client hello and server hello. These traffic secrets protect the rest of the handshake messages. From each traffic secret, we derive an encryption key and an IV, so we end up with 4 values: client handshake key, client handshake IV, server handshake key, and server handshake IV. Then we move to the master secret stage. We derive another derived value from the handshake secret, and we use HKDF extract with this derived value as salt and zeros as IKM to create the master secret. The master secret inherits all its security from the handshake secret through the salt. From the master secret, we derive client application traffic secret 0 and server application traffic secret 0 using HKDF expand with labels and including the full transcript hash of the entire handshake. From these application traffic secrets, we derive the client application key, client application IV, server application key, and server application IV. If you count them up, we used HKDF extract 3 times, once for early secret, once for handshake secret, and once for master secret. We used HKDF expand many times. For derived values, for traffic secrets, for keys, and for IVs. Each HKDF operation is carefully designed with specific inputs. The salt for each extract operation comes from the previous stage. The labels for each expand operation are chosen to create separation between different keys. The transcript hashes bind keys to specific handshake conversations. This entire chain ensures that keys are properly derived and properly separated. The beauty of this design is that it is deterministic and symmetric. Your browser and the website both do the exact same HKDF operations in the exact same order with the exact same inputs, so they both arrive at the exact same keys. But anyone watching the connection cannot compute the keys because they do not know the ECDHE shared secret. They see the public keys in the hello messages, they see the encrypted handshake messages, and they see the encrypted application data, but they cannot decrypt anything. The entire security of TLS 1.3 rests on the mathematics of ECDHE and the careful application of HKDF. Why this design is brilliant. Now that we have seen the entire HKDF chain in TLS 1.3, let us talk about why this design is so brilliant. The designers of TLS 1.3 made many careful choices that make the protocol secure, efficient, and elegant. Understanding these design decisions will help you appreciate how much thought went into keeping you safe online. First, the hierarchical key derivation structure is brilliant. TLS 1.3 doesn't just hash the ECDHE shared secret and use it directly as the encryption key. Instead, it creates a tree of secrets, with each level serving a different purpose. The early secret stage handles optional PSKS. The handshake secret stage brings in the ECDHE entropy. The master secret stage separates handshake protection from application data protection. Each traffic secret is then expanded into specific keys and IVs. This hierarchy provides defense in depth. If one level is somehow compromised, the other levels are still protected. Second, the use of transcript hashes for context binding is brilliant. By including a hash of all handshake messages in the derivation of traffic secrets, TLS 1.3 ensures that any tampering with the handshake will be detected. If a man-in-the-middle attacker tries to modify the handshake messages, the transcript hash will be different on the client and server, so they will derive different keys, and the connection will fail. This prevents downgrade attacks where an attacker tries to force the use of weak cipher suites. Third, the separation of client and server keys is brilliant. By using different labels to derive client and server traffic secrets, TLS 1.3 guarantees that the keys are different. This means that if the client's key is somehow compromised, the server's key is still safe. It also prevents reflection attacks where an attacker might try to replay messages from the client back to the client by pretending to be the server. Fourth, the use of HKDF instead of simpler derivation methods is brilliant. HKDF provides a standard, well-analyzed way to derive keys. The extract phase ensures that even if the input key material has some structure or bias, the PRK will be uniformly random. The expand phase allows deriving multiple keys from one PRK with proper domain separation. This is much better than just hashing the shared secret multiple times, which might have security issues. Fifth, the deterministic nature of the key schedule is brilliant for implementation. Both the client and server follow the exact same recipe, so they end up with the same keys. There is no ambiguity and no room for implementation errors. The key schedule is fully specified in the TLS 1.3 standard document, and any implementation that follows the specification will interoperate correctly. This makes TLS 1.3 easier to implement correctly and easier to test and verify. The fact that billions of TLS connections happen every day without issues is a testament to this good design. Summary and key takeaways. We have learned so much about how TLS 1.3 uses HKDF to create encryption keys. Let me summarize the key points so you can remember the important ideas. TLS 1.3 is the protocol that protects your data when you browse websites, and HKDF is the key derivation function that turns shared secrets into encryption keys. Together, they keep billions of people safe online every day. First, remember the hello messages. The client hello and server hello exchange includes random nonces and ECDHE public keys. Both sides compute the same ECDHE shared secret using their private keys and each other's public keys. This shared secret is the source of entropy that makes everything secure. Bad guys watching the connection see the public keys but cannot compute the shared secret without breaking elliptic curve mathematics. Second, remember the three-stage key schedule. Stage 1 creates the early secret from zeros just as a starting point. Stage 2 creates the handshake secret by extracting with the ECDHE shared secret, bringing real security into the system. Stage 3 creates the master secret to separate handshake keys from application keys. Each stage uses HKDF extract to create a new level of the hierarchy, with the salt coming from the previous stage. Third, remember how traffic secrets and keys are derived. From each master secret, we use HKDF expand with different labels to create client and server traffic secrets. The labels provide domain separation, so keys for different purposes are guaranteed to be different. The transcript hashes bind keys to specific handshake conversations, preventing tampering. From each traffic secret, we derive an encryption key using label key and an IV using label IV. Fourth, remember why zeros as input to HKDF extract still produce secure outputs. HMAC uses XOR with IPAD and OPAD internally, so even zero inputs go through complex transformations. The early secret from zeros is not a secret because everyone can compute it, but that is fine because it is just a placeholder. The real security comes from the handshake secret, which includes the ECDHE shared secret. The master secret uses zeros as IKM, but the salt comes from the handshake secret, so it inherits all the security. Finally, remember that this whole system is deterministic and symmetric. Your browser and the website both follow the same recipe and arrive at the same keys. But bad guys watching the connection cannot compute the keys because they do not have the ECDHE shared secret. The combination of strong mathematics for ECDHE, careful protocol design for the key schedule, and proven cryptography for HKDF makes TLS 1.3 one of the most secure protocols in the world. Every time you see that lock icon in your browser, you can feel confident that this amazing system is protecting you. Thank you for your attendance. Please consider subscribing to the channel.